So let's begin with lecture 6 of the course on galaxies. So this is where we had stopped the last time. We started talking about the large scale structure of galaxies. We said that we've so far looked at galaxies as individual objects on the size scales of about few tens of kiloparsec. But galaxies are also very effective tracers of the large scale structure of galaxies, which of course is the ordering of baryons, the clustering of baryons on megaparsec scales or larger. So just as stars are the building blocks of galaxies, galaxies themselves are the building blocks of this cosmic web of large scale structure. It's a three-dimensional structure, gives rise to various structures like filaments and voids and clusters and so on. But you have to constantly keep in mind that galaxies are biased tracers of the underlying dark matter distribution. So if you want to compare the dark matter distribution that you get, for example, from numerical simulation with the distribution of galaxies, you have to assume or model the what is called as the galaxy bias, which is the ratio of the baryonic mass of the galaxy to the dark matter, to the total mass of the galaxy. And that is not constant. That is a function, as we shall see when we study dark matter in galaxies, that it's a function of various things, including the baryonic mass of the galaxies. In general, a thumb rule is that at lower stellar masses, the fraction of baryonic mass is smaller. That is, dwarf galaxies have a large amount of dark matter within them than, let's say, massive galaxies like the Milky Way. So in order to study or observationally see the large-scale structure of galaxies, you need to carry out galaxy redshift surveys. And why do we need to do this? Because we know that density fluctuations evolve into the structures that we observe, the galaxies, the clusters, etc. So in order to map them, you have to do a galaxy redshift survey. So what are the structures that you expect to see when you do a large-scale structure survey? You expect to see galaxy groups, like the local group in which we sit, galaxy clusters like the Coma cluster or the Virgo cluster or the Fornax cluster and other clusters. You expect to see filaments. So filaments are like thin strands of matter that connect possibly one cluster to another. Then you expect to see walls. Walls are like filaments, except that they are two-dimensional rather than one-dimensional. Then you expect to see voids. You expect to see regions of space in which there are few or very few or no galaxies. But you also expect on the other side to see superclusters, which are literally clusters of clusters. Many clusters together in one small volume are called as a supercluster. All of these are the elements of the large-scale structure. And obviously, to map and quantify the large-scale structure and to compare it with the theoretical predictions of cosmological models, we need redshift surveys. And what do? Redshift surveys basically map for you the 3D distribution of galaxies. The 2D distribution, very easy. You just do any imaging survey, you get the two-dimensional distribution of galaxies. But in order to get the third dimension, the distance to the galaxy, you need to do a redshift survey. And these have been going on. Galaxy redshift surveys have been going on in a systematic way for more than 50 years now. And today we have redshifts measured for more than 2 million, probably more than 3 million galaxies now. While the existence of clusters was recognized early on, it took a while to recognize that the galaxies are not distributed in space uniformly and randomly, but in coherent structures. Okay, so you may suddenly, thought may come to mind that why are we saying galaxies, etc., clusters? Because we have studied in cosmology that the universe is homogeneous, isotropic, etc. But remember, it's homogeneous, isotropic only on very large scales, hundreds of megaparsec to gigaparsec scales. Yes, the universe is homogeneous and isotropic. But if you go to scales of, let's say, 10 megaparsec or 5 megaparsec, then the universe is most decidedly not homogeneous. Okay, but both these statements are consistent. On very large scales, cosmological scales, the universe is homogeneous, but on smaller length scales, the universe is not homogeneous. So before you do galaxy redshift surveys, you have to
Sir,
yeah,
sir.
go ahead.
So if the universe is isotropic and homogeneous, then why the structure is not also isotropic?
Sorry, why is the
Why the distribution of the galaxies is not isotropic?
it is isotropic on the largest scales. Okay, so if you take galaxies located only, let's say, within 10 megaparsec of us, then it is not isotropic, because you will find at 16 megaparsec you will find the Virgo cluster, which will be
So up
in
to
direction of Virgo.
what length we should go to assume
I
the?
think you should keep, if you want the universe to be homogeneous, you should not have a box size smaller than about 100 H inverse megaparsec. Okay, if you stick to that length scale, you're okay. Moment you come below that, there are special places in the universe where things will look different than the average.
So only we should consider the length, right? Other
Yeah,
factor.
length scale that defines for you a size, a cubic box. So that's why you will find that cosmological simulations are always done with box sizes which are very large, 100 megaparsec, 200 megaparsec, even gigaparsec. You don't want a cube which is less than that on a side, because then you're not able to study things on average, which you want to in the cosmological simulation. Does that answer your question?
Yeah, but if we are making any model,
Yes.
then in that model, is there any other parameter that we can tune instead of this length scale to make it homogeneous?
No, the length scale is defined in terms of the Hubble's constant and the size. So that's why I said 100 H inverse megaparsec. We'll come to that discussion a little bit later.
Okay.
Just hold your question. So in order to do your galaxy redshift survey, first you have to do an imaging survey, because you have to first identify the galaxy whose spectrum you want to obtain. So this started in a systematic way around 1970. There was a systematic way for galaxies. Earlier, there used to be a large area photographic sky surveys, but they were mainly focused on just stars and everything else. I mean, it was just a general purpose survey. But where people started saying that, no, we are only interested in galaxies, that started with this LIG survey, which had about 1 million galaxies. These, remember, are photographic surveys. Until about the year 2000, everything is a photographic survey. Then it suddenly becomes digital. In 1990, there was the APM survey, which had 2 million galaxies in it. By 1995, DPOS. So in the 1950s, there was a large survey carried out with one telescope in the northern hemisphere and another telescope in the southern hemisphere, using photographic plates and Schmidt camera type telescopes to actually just image the entire sky. This was known as the Palomar Observatory Sky Survey, which is one of the most famous sky surveys conducted. Of course, since they observed everything, every square degree of the sky was photographed, and over a period of a number of years, and those plates were available. And when I joined IUCAA in 1994, we actually had glass plates which were reproductions of those Palomar plates. So there was a machine on which you could place the plate, and with a magnifying glass look at the sky. But by 1995, a big project had been carried out called the Digitized Palomar Observatory Sky Survey. So people said that, no, this is very inconvenient, all these glass plates and all. Let us just use a scanner and let's just scan the whole sky, and we'll make it available to people. DPOS was first, DPOS and the earlier digitizations with an APM machine were available on CDs. Okay, and then DPOS was, I think, the first one that also became quickly available on not just on CDs, but it became available on the internet. So this truly was the start of internet data downloads in astronomy. By 2005, the Sloan Digital Sky Survey had completed its first iteration, and now we suddenly had 200 million galaxies. By 2024, we will take another leap. There is going to be the Rubin telescope and the Large Synoptic Survey. Actually, it's now called the Large Survey of Space and Time, which is a synoptic survey with the Rubin Observatory, and that is going to detect sample of 10 raised to 10 galaxies. Okay, so 10 billion galaxies. Sorry. Synoptic means where you observe the time evolution. So it's, you observe the same part of the sky multiple times, separated by some time interval, so that if there are any moving objects or there are objects that are variable, you'll be able to study that. So that is called synoptic, the time varying component. So to study the synoptic universe, this is a dedicated survey called LSST, which will start in a couple of years. And we have people from both IUCAA and NCRA who are members of this survey now, foreign collaborators of this project. So some of you may get to work with LSST in the future. Okay. So of course, spectrographic observations of galaxies go back to the 1910s. But these were usually done by small groups of people observing small samples of galaxies, 10 galaxies, 5 galaxies, like that. But by 1985, the first systematic large area spectroscopic survey of galaxies had been carried out at the CFA, and they observed 2,500 galaxies in their work. Soon afterwards, there was the CFA2 with 20,000 galaxy spectra. And around the same time was another Redshift survey called the Las Campanas Redshift survey, which was so named because it was carried out at the Las Campanas Observatory in Chile. And they got 23,000 spectra. But really, the explosion came in the digital age. The 2DF galaxy survey was completed in 2003, and they got 250,000 spectra of galaxies. By 2005, the Sloan Digital Sky Survey Spectroscopy was in full swing, and they had obtained about 800,000 spectra of galaxies. And the most recent iteration of the Sloan Digital Sky Survey, data release 17, has more than 3 million spectra of galaxies. So within the last 25 years or so, we have seen a 100-fold increase in the number of spectra that are available. Yeah. Sorry? Yes, because it's much harder. Okay, that's a very good question. Why is it less? It's less because when you do spectroscopy, you have to spread the light out. Okay, and if it's a very faint galaxy whose spectrum you're trying to obtain, then you have to take the spectrum for a very large period of time. So for example, in the Sloan Digital Sky Survey, every spectrum is taken for about 1 hour. So it takes a large amount of time. Whereas if you want to take an image, again, if you say the Sloan Digital Sky Survey, you can get an image of the same galaxy with very high signal to noise in about 1 minute. So that is the ratio. It is about 100 times harder to get a spectrum just in terms of telescope time and therefore in terms of cost And therefore, most spectroscopic surveys are of typically 100 times, samples are 100 times smaller than the equivalent imaging survey. So that's true for the SDSS, for example. I told you there are 200 million galaxies in the SDSS and about 3 million spectra. So just over 1% of objects have spectra, just because of the investment. Nowadays, people have started doing integral field spectroscopy, wherein you take a spectrum not of the galaxy as a whole, but you take a spectrum of every pixel in the galaxy. So these are called now spaxels. We'll see 3D spectroscopy when we do dynamics. And so you get, that is even more expensive, because not only are you spreading the galaxy's light into multiple pixels to get a spectrum, you're first spreading it for different pixels of the galaxy. You may have 100 spaxels, 200 spaxels on the galaxy, and you're spreading it out. So which means you have to integrate quite long. That is the reason why the spectroscopic surveys are always going to be smaller than the imaging surveys. Okay. So now what did these surveys reveal to us? So first of all, they mapped out for us the local group. So as I've said already, I think once previously, the local group consists of only 3 large galaxies, the Milky Way galaxy, the Andromeda galaxy, and the Triangulum galaxy. And the size scale is of the order of 1 megaparsec. Okay, that's the size of the local group. The local group has only 3 big galaxies, but it has a very large number of dwarf galaxies of the order of 30. I don't remember the exact number, but that number keeps on going up every few years as newer dwarf galaxies are discovered. So we are absolutely sure there is no big galaxy in the local group, but there could be additional maybe 5, 10, 15 more dwarf galaxies which are part of the local group. And why is it? Why are we discovering these dwarf galaxies now? It's not so much the fact that they're faint, which they are, but they are often located in directions in which the foreground of Milky Way stars is very, very bright, or the amount of Milky Way dust is so thick that it is obscuring everything. So for these 2 reasons, it becomes in certain parts of the Milky Way, in the disk of the Milky Way, for example, it becomes very difficult to identify dwarf galaxies. So that is why you have to do some complicated techniques in order to identify them. That's why we are identifying them. If they were located in a different direction, they would have been found. And as we saw, these dwarfs, some of them are irregular, some of them are spheroidals, some of them are dwarf ellipticals, and so on. So they are different morphologies. Of course, the nearest dwarfs to us are the 2 Magellanic Clouds, the large and the small. Okay, so if you go to a larger scale, okay, now we've changed the scale by about a factor of 10. So for scale now, the distance from us to Andromeda is about 800 kiloparsec. The distance from us to the Virgo cluster is about 16 or 17 megaparsec. Okay, so it is about, let's say, 20 times further away than Andromeda. So if you want to imagine that distance. So here's the local group now again at the center of this image. And on this side is the Virgo cluster, and then there is the Fornax cluster, the Eridanus cluster, and so on. In addition to that, there are other groups. So for example, there is the Ursa Major group, the Leo group, and so on. These objects are sufficiently close to each other that they can be considered as the local supercluster. Okay, all of them are part of the local supercluster. We know that the sun is not in a privileged position in our galaxy. Okay, it's not right at the center or right near the edge or anything. It's not special in any way. In terms of mass also, it's not a special star at all. There are billions of stars, sun-like stars in our galaxy. But our galaxy is in a privileged position in terms of mass. The Milky Way is a massive luminous galaxy. It is not an ordinary galaxy. It's not an average galaxy. Similarly, our environment, our immediate environment, seems to be a little bit more special. The probability of having a cluster as massive as the Virgo cluster, so close to us, 16, 17 megaparsecs away, is quite small. Okay, so we are definitely, in terms of the galaxy we sit in and in the supercluster we sit in, we are in a somewhat privileged position, somewhat special, extreme position. People are trying to work out whether this has any implications to formation of life. Could life form as easily in dwarf galaxies, or could it form in voids and so on? We don't know. Okay, so just like we have our local supercluster, there are a number of other superclusters. The Perseus Pisces supercluster, the Hydra supercluster, the Leo supercluster, and so on. They're all labeled here. Now we've zoomed out again by about a factor of 100. Now we are looking at things on scales of hundreds of kiloparsec. Okay, this is the scale that you see here is 100 million light years, okay, which means about 30 megaparsec. So if you go from one edge to the other, you probably have about 200 megaparsec box. It is on this length scale that the universe becomes homogeneous. On any smaller length scale, it is not homogeneous. So clusters, superclusters, etc., are very common. But remember, it's homogeneous only in the nearby universe, right? If you look at the very distant universe, 100 megaparsec co-moving box will not have as many clusters and superclusters that we see today. These are things, structures of galaxies that have also formed relatively recently. So just like the Hubble sequence has all formed relatively recently, the clusters and superclusters that we see in the nearby universe are simply not there in the high redshift universe. There are protoclusters and proto-superclusters in the high redshift universe, which over time will evolve into the large-scale structure that we see today. Okay, right. So now there is another view you can take, which is just plot with a dot the 6,000 brightest galaxies that you see in the sky. Now, this is a two-dimensional map. You're not worried about the distance, okay? And then you see some obvious places where there is clustering, okay? Some of these are clusters like the Coma cluster, the Virgo cluster, and so on. And some of these are superclusters like the Perseus Pisces supercluster and so on, and the Hydra supercluster. Okay, so where would the 6,000 brightest stars in our Milky Way lie in this picture? Where do you think they'll be? Yes. Yeah, that's the plane of the Milky Way, correct. And I told you it's very hard to see galaxies very close to the plane of the Milky Way. So where will the stars lie? In the disk. So they will actually lie, if you plot the 6,000 stars in the Milky Way, they'll mostly lie here. Right? So that's it. So this forms the two-dimensional large-scale structure, but it's important in order to do cosmology or to test the predictions of cosmological models to convert this into a three-dimensional structure, and that requires your redshift surface. So here's a map from the CFA spectroscopic survey of a region around the coma cluster. Okay, and this particular structure, it looks like a man with one leg here and one leg here. So this is called as a stick man, the CFA stick man. Initially, people thought, what is this? Why is there a structure that's aligned perfectly in the radial direction? Is there something special going on here? Turns out not. This kind of stretching along the radial direction has happened because these objects are so nearby that the peculiar velocities of these galaxies within the cluster are a large fraction of their Doppler recession velocities. And so because of that, some galaxies are moving towards you, some galaxies are moving away from you, and so on. So that gets stretched. This plot gets stretched in the radial direction. So what's plotted here along the curve is the right ascension of the galaxies, and what is plotted along the radius is the recession velocity. Okay. You can of course correct for the peculiar velocities once you model the cluster mass, for example. If you know the cluster mass, you know what will be the peculiar velocities of galaxies. And then you can take that out and make a corrected, velocity corrected, peculiar velocity corrected map of the same thing, which has also been done. But notice here is that you can't really see the large scale structure. The only structure you see is that artifact, and you see another smaller man over here, but this is also an artifact caused by the radial stretching due to peculiar velocities. Once you take that out, you can't really see the large scale structure. And that is because we are not looking far enough. Okay, so you need a deeper redshift survey with more galaxies in order to begin to see the cosmic web. So the first hint of the cosmic web came here with the last Campana's redshift survey, which, as I told you, had about 23,000 galaxies in two different regions of the sky. And there you begin to see, of course, squashed version of the three-dimensional structure with about 23,000 galaxies. Yeah. So you have to know what the peculiar velocity is. You don't, we only know the radial component of that velocity. But assuming that the radial component is not a preferred direction, you can make a statistical average of how much radial velocity should be there, given its randomized. See, remember, it's going to be falling towards the center. It doesn't. It's either falling towards the center or has crossed it and gone on to the other side. The galaxies are not going around in circular orbits, for example. So you know that much. So that they're very, very highly elliptical orbits, which take them very close to the centroid of the mass centroid of the galaxy. So since you know that, and you know how fast you have to measure the cluster mass. Measuring the cluster mass itself is tricky because you have to. We will see later on in the course how that is done, because remember, you can't just take the galaxies and measure their mass. There'll be dark matter in the cluster itself, in the intracluster medium, in the galaxies, everywhere. So you'll have to use the kinematics of the galaxies in order to model the mass of the cluster. Once you know the mass of the cluster, you will know a galaxy at a certain position, what kind of peculiar velocity it is expected to have. And then you can take that out. So it's a bit tricky, but by doing careful mass modeling of the cluster and by measuring the the radial component of the velocity for as many galaxies as you can. And for massive clusters like Coma and so on, you can measure the redshifts of 1,000 galaxies. So you will have lots of data points in order to constrain the mass model. What are those bands? So what they've done is they are in different declination ranges. Okay, you see this -39, -42, -45, etc. What they've done is they have over here they've combined all of them together, right? And there they've tried to show you by only combining them separately, but really squishing them, that entire velocity thing has been squished into a small thickness over here.
They have squished the declination part with
Declination is squished in all of them.
yeah, and over here they have
Squished in velocities. Las Campanas is located in Chile, in the southern hemisphere. So they are able to observe galaxies in the southern hemisphere easily. That's why they've not done the northern galaxies. Same would hold true if it were in northern hemisphere, they would all be northern galaxies, not southern galaxies. Which band? No, this is just a squished version of this, but separately. Just if you want to see whether there is more clustering at declination -39 versus -45 and so on. Okay, so this is just to indicate. Also, they don't have sky coverage in certain parts. So, for example, at this declination range over here, there's a gap. Okay, in other places over here, it's a gap. So this is just a pictorial representation. If you want to do statistics with it, of course, you have to use all the individual data points. This is just a graphical representation. Okay. So with the advent of digital sky surveys, one more very important innovation happened. Until we did the older generation surveys, the spectroscopy was not multiplexed. What I mean by that is that so the telescope would point to one galaxy, they collect the light from there, and then they would spread out the light through a prism or grism or whatever there is, and they'll get spectrum of one galaxy at a time. With these digital sky surveys like 2DF and SDSS, they decided that no, this is very inefficient. We'll point the sky in a particular, the telescope in a particular direction of the sky, and if there are 100 galaxies there, let us collect spectra of all 100 objects at once. So what they would then do is, with the SDSS, they would put what is called as a plate, and in that plate they would drill holes. So it's an aluminum plate in which there are 100 galaxies. At those 100 positions, they will drill 100 holes, and they'll connect an optical fiber in each of those holes. They'll collect that light and then take it to the detector. So the efficiency improved 100-fold. So much of the increase of galaxy spectroscopic samples in numbers has increased not because we had bigger telescopes or better telescopes, but because we had massively multiplexed spectrographs. So the original SDSS spectrographs could do 640 spectra at one go. And then they improved it. In the next generation, they could do 1,000 spectra in one go, and so on. So now, again, it improves. There is a recent survey, spectroscopic survey, which has just started, which is called DESI, Dark Energy Spectroscopic Instrument. And that survey has 5,000 simultaneous spectra. Takes 5,000 spectra in one. Not only that, in the old surveys, you had to do imaging, then you had to drill an aluminum plate to move, to place the optical fiber in, and that took a long time. And for every part of the sky, you had to drill a different plate. Now they've said that's too time consuming and expensive. Let us have little robots that can move the optical fiber to any position we want. And it can do it within a few minutes. Okay, so you do 5,000 spectra in an hour. Then in 3 minutes, you rearrange everything, move the telescope, you rearrange everything, and you have 5,000 more positions, take 5,000 spectra more. So that allows them to get, I think, about 20,000 spectra per night. So that is going to lead to another manifold increase in the number of galaxy spectra. Yeah. Yes. Yeah. Yeah. Yes. So one thing is cost. Okay. Because if you have 50,000 fibers, you have to have a detector that can image 50,000 fibers at one time. Okay. That is prohibitively expensive. So that's why we don't do it. And most of the fibers will lie on blank sky. There won't be any galaxy there. So you won't get any useful information. So you are putting in a lot of effort, but you're not getting that much new useful information. That's why it's better, because remember, at whatever level you image only the brightest galaxies in the field. So you do 5,000 galaxies, you do the 5,000 brightest objects in the sky. If you wanted to do everything, you would have probably need 50,000 fibers. You don't have the technology and the money to do that. But what you are suggesting is an integral part of what is called integral field spectroscopy. So there you say that, okay, I have one big galaxy. And can I, instead of taking a spectrum only at its center through one optical fiber, can I bundle many optical fibers together and together place them on the galaxy? And that is called integral field spectroscopy. The bundling of fibers is one technique, one way of doing this, and people are doing it. There are very large surveys with the SDSS, for example. There is a survey called Manga, which has just finished doing 10,000 galaxies, with each galaxy with a bundle of fibers. So they're all just like, as you suggested, just put one fiber next to each other and stick them together. That is done. And they have up to 127 fibers in one fiber bundle. So you get 127 spectra in one go of one galaxy. Okay, yeah. Nice question. But once you go to sufficiently high redshifts, the peculiar velocities, remember, even in peculiar velocities in clusters are of the order of 1,000 kilometers per second. Okay. But once you go to velocities which are much, much larger than that, because the redshift is much larger, then the peculiar velocity becomes a small fraction of the total velocity. And then you can ignore it. In fact, you have to ignore it, because correcting for peculiar velocities requires you to build a model for the peculiar velocities, which is very difficult and time consuming. Okay. So at redshift 0.5, you don't care about the peculiar velocity. It is 1,000 kilometers per second is nothing compared to the actual recession velocity, the doubly shifted velocity. Yes. Yes. So for individual clusters, you can correct it. So suppose you're interested in this one cluster, which is at, let's say, medium redshift, but is so massive and big that the galaxies are moving very fast. You may have one such cluster. And for that, you can go ahead and build a mass model and so on. So when you do a galaxy redshift survey like this, it is not being used only for studying the large scale structure. It may be used to study clusters themselves or the distribution of cluster mass and so on. So different people are doing these things from the same data. Right now, since we are only looking at it with blinkered eyes, we are only looking at the mapping of large-scale structure. We will come to studies of galaxy evolution with redshift surveys later on. Right now, we are just saying what is the distribution of galaxies in the universe on large scales. Yeah, but what you asked is a very important question. Okay, now next question. So people thought, okay, we did this with optical redshift surveys. Can we do this kind of thing with study the clustering with radio data? So what is shown here is every dot that you see in this picture is a galaxy from the NVSS sky survey, which was a survey done with the VLA telescope about 25 years back, a new VLA sky survey. And this is the distribution on the sky. Okay. But here you see that the distribution is not clustered at all. So for example, if you compare with this, where you see clear signal of clustering, it's not a random distribution. This seems to be pretty random. Why is that? Any guesses? You're only seeing the radio galaxies, correct? But if radio galaxies are clustered in the same way as optical galaxies, then you should see some signal there. Yes, it is biased in some way. That is correct. Now you have to tell me in which way is it biased. Huh? Sorry? No, not really. It goes very faint. It's a very sensitive survey. There are, I think, 2 million sources are there. 2 million galaxies. Sorry? In clusters, there are more radio galaxies, yes. That is true, but that doesn't explain this lack of clustering already. Yes. In what way? Angular resolution is, let me say, is quite poor relative to radio galaxies. But there's one more factor. So I'll tell you, I'll give you a hint. Unlike these galaxies, which are relatively close, they are at redshift less than 0.1, for example. Most of these redshifts of these sources are at redshifts of 0.7, 0.8, like that. Sorry? Before structure formation, yes, but probably just a resolution effect. See, what has happened is you're seeing the large scale structure because you're sufficiently close and you can see the variation in the density of galaxies. But if you are I take this Coma cluster, Virgo cluster, whatever, put it 1,000 times further away, it'll all get smoothed out. Yes, yes, yes. And so because of that, the universe is actually quite isotropic in the radio. You count the number of radio sources per square degree and you compare it with any other direction, you'll find that it's almost uniform. There are some Poisson fluctuations, but the mean is fixed. It will change, the mean will change if you do a more sensitive survey, but the direction in which you observe, there is no signal there, because your length scales that you're probing with each element are very much larger than what you are probing in the optical. And therefore, everything is getting smoothed down. Why is it at this redshift? Because of two reasons. So radio surveys are very counterintuitive. If you do a radio source survey and you put a flux limit of, let's say, 100 millijansky, you say that at 1.4 gigahertz, any source brighter than 100 millijansky, I will detect, okay, and I will study. So you make a survey, you do study, you identify what these objects are. You will find that all of them will be AGN, 100%. If, on the other hand, you do another survey which is 1,000 times more sensitive, which goes to, let's say, 0.1 millijansky at 1.4 gigahertz, and then you'll obviously be dominated by fainter sources now. Number of sources will increase. You try to find the median redshift of those faint sources. You'll get a median redshift of 0.1. So in the radio, in the optical, the fainter objects are further away. In the radio, the fainter objects are closer. Okay, and why does this counterintuitive thing happen? Why could it happen? Most, that is true, but yeah. So this is just a median redshift. It's not that everything is at 0.7. Something could be at 0.4, 0.8. Everything is there. Their numbers are higher. That is true as you go to higher redshifts. And with the kind of sensitivities that we are reaching, we are able to probe up to 0.7 or so. They'll go even higher if you go further out. But this doesn't explain the question I'm asking. Huh? Sorry? How does that affect anything? See, the thing to think in terms of physics. So AGN are becoming less active, so there are fewer AGN. So then there must be some other mechanism, right? So do you get radio emission only from sources? That is true. Correct. Correct. So that is true. So there will be a Malmquist bias, which means that your low redshift sources are low luminosity sources. High redshift sources will be typically high luminosity sources. Correct. Now, so what is this low luminosity population at low redshift which appears in your survey if you do a sensitive survey? Not in our own galaxy, nearby galaxies. There are very few continuum sources in our galaxy. There are some supernova remnants and so on, but only a handful. Almost everything is outside our galaxy. So what is it? So can you think of a non-AGN mechanism for radio emission from galaxies? Sorry? Pulsars, yes, but they're very weak in the continuum. Sorry? 21 centimeter, that will give you neutral hydrogen, but that's doesn't give you, again, that's emission in a line. What causes continuum emission from a non-AGN source? Yes, but from where? Caused by what?
Jets.
That could be one, but much more common is synchrotron emission from star formation related processes. So even if you have one supernova going off, that pumps in so much energy into the interstellar medium that it accelerates sufficient number of charged particles to relativistic velocities. They eventually cool down, etc. They're constantly radiating. So if you have a star formation in a galaxy, that is another mechanism by which you can get radio synchrotron continuum emission from the galaxy. But that is much weaker than, in terms of the luminosity, it's weaker than the emission you get from AGN. That's why the AGN you can detect up to redshift of 0.7, 0.8, 1, 2, etc. But the supernova or star formation driven synchrotron emission is so weak, we can only detect it with present generation radio telescopes up to redshift of 0.1. And those begin to appear. So star forming galaxies begin to appear in your radio source sample only at low radio flux levels corresponding to small distances and low luminosities. So if you did a more sensitive survey, very sensitive survey where you were dominated by the low redshift radio sources, then you will see clustering in these. This is just things very far away. Okay. Then the massively multiplexed spectroscopic survey from the Sloan. So here again, it's like the 2DF signal. It goes roughly to the same depths as the 2DF. These are from the original 800K spectra that were obtained by 2005, but now they've tried to continue mapping the large-scale structure to larger distances in two ways. Okay, one way that they have used to extend the large-scale structure of the universe is by studying what are called luminous red galaxies. So these galaxies are typically sit in very high density regions of the universe in clusters, and they can be used to map the clusters in the high redshift universe. Because they are more luminous, even with the same telescope and instrument, you are able to detect them to redshifts of 0.3, 0.4, and so on. Most of the other SDSS galaxies go only up to, you can see they've got redshift over here. So you'll see that after redshift 0.1 and definitely after redshift 0.5, your cosmic web is disappearing. Not because there are no galaxies there, but because you don't have enough sensitivity to observe those galaxies. The telescope is not powerful enough. So we are only able to trace the low redshift large scale structure up to redshift of 0.1 or 0.15. After that, serious incompleteness comes in. So if you want to trace the structure over here at redshift, let's say 0.3 or 0.4, you have to use luminous red galaxies, but that's a biased tracer. Okay, because these are only allows you to map the highest density regions of the universe, nothing else. So as an alternative, they said that we'll do one more thing. We'll pick quasars that are very distant, redshift 1, 2, 3, etc. And we will look for quasar absorption line systems along the line of sight to thousands of quasars. And then what we will see, so suppose there is a very faint galaxy, which is whose emission you are not able to see directly, or even if you are able to see directly, it's too faint to get a spectrum. If that galaxy lies along the line of sight to the distant quasar, what's going to happen? Absorption line will get produced. Hydrogen will be there, for example. It'll absorb. Other metals may also do produce absorption lines. Mg2 absorbers are very commonly used metal line absorbers in the study of these sort of faint galaxies and their distribution. Yeah. You cannot do a perfect job. You cannot do a perfect job that you're doing at very low redshifts with the SDSS, right? But you can still get many more lines of sight than you can with the luminous red galaxies. Those are really sparsely distributed in the sky. Quasars are much more common because they're just sampling a very large volume. With the SDSS now, I think we have more than 100 quasars per square degree. So in every square degree of the sky, you can have 100 lines of sight. Of course, they have chosen some quasars which have properties that help them that fit their selection function. So you can't do as good a job as you can do at zero redshift, but you can do a better job than nothing at all. And there are enormously complicated statistical techniques available now to correct for your biases. So everything is biased. You just have to understand what the biases are and try to correct for them. So there are all kinds of corrections for both stochastic, I mean, mostly for stochastic biases, not non-stochastic biases, the systematic biases that are present in your data, you correct for it. And you try to carefully estimate what are the random biases in your data so that you can estimate what is the error bar in your measurement. Yeah. Yes. Yes. They see some of these surveys are very large, like the SDSS, for example, covers 1/4 of the sky already, right? To do a survey in the southern hemisphere, which will cover, let's say, another 1/4, some parts of the sky are inaccessible because of the galaxy. That I think you lose about 20% of the sky. You don't do extragalactic surveys. The rest 80% you can do. And so they could do it with another survey in the southern hemisphere. But if our generic overall assumptions about homogeneity and isotropy are true, then there shouldn't be a difference. You do the one more survey. Remember, this Sloan Digital Sky Survey started in 2000. It's still going on with various iterations. That you can do a large area survey. There is no problem. Yeah. Then you can. There's no problem. But remember, the structures are not that large. See, suppose you are doing a survey that's covering 60 degrees of sky. Only at the edges you will have a problem with the large scale survey. But you will see enough examples of similar structures within your survey. So you're not going to find something drastically new by just observing over the edge. Right? That's why we do. But you can. For very low redshift surveys, you don't have to, since your one telescope has done northern sky nearby galaxies, you can combine it with southern sky nearby galaxies. Hard to do at higher redshifts because it's very expensive. These are faint galaxies. Okay, so a number of surveys have been carried out in recent years, and some of them are coming in the near future. So this is a plot in which what is shown on the x-axis is the area in square degrees of the redshift survey, and on the y-axis is the density of spectra, which is the number per square degree. So obviously, ideally, you want very large area and very large density. You want to be here. The telescope that is going to get us there in the near future is a space telescope called Euclid, which will not get very accurate redshifts because it uses a photometric redshift technique, but it will literally observe spectra. One single telescope will exceed what SDSS has done in 20 years within a few years. So it's very exciting. What we have now is 1 million plus redshift surveys from a survey called BOSS, Baryon Acoustics Sky Survey. Baryon Oscillation Sky Survey, the acoustic oscillations. This is part of SDSS. This is one of the recent SDSS surveys. So that itself has, and then there are various SDSS Luminous Red Galaxy survey and so on. So there's several SDSS Stripe 82, etc., etc. And the 2DF Galaxy Redshift survey sits here. And as you can see, people are over the years have been trying to move from this corner of the diagram to that corner of the diagram, trying to do large area surveys with a very high density of spectra. Yeah. How do you determine redshift photometrically? Okay, so I'll respond as briefly as possible. So you know how to determine redshift with lines, right? With emission lines and absorption lines. You know what is the laboratory value of a particular line. You observe the spectrum, find out how much it has shifted. That gives you the redshift. Now, remember the spectrum of any object, be it a star or galaxy, has a certain continuum shape, which is well understood. And if you know the morphology of the galaxy, you know what is going to be the continuum spectral energy distribution of ellipticals, what is it going to be for spirals, and so on. What is it going to be for irregulars, etc. So if you assume that you know the spectral energy distribution, then you can fit, not for lines, but you can fit the continuum by observing the continuum at different points in its distribution. So you make a, let's say, UV light flux or optical light flux, mid-infrared, near-infrared, etc. And then you compare that flux with the predicted flux of the redshifted galaxy. So suppose you happen to know, yeah, I don't know the redshift of this galaxy, but it's surely an elliptical. So I will fit a elliptical spectral energy distribution template to the broadband fluxes of this galaxy, and I'll tweak the redshift. So I basically move the continuum spectrum left or right until I get a good fit to the data. And that is my best fit photometric redshift. It's much more unreliable as expected compared to spectroscopic redshift. Spectroscopic redshift, if your signal is strong, then only if you make a mistake in the identification of the lines, you think it is Lyman alpha, but it is actually H alpha or something drastic like that, you will not make a mistake in the redshift. It's very accurate. But in photometric redshifts, because that template spectrum is not perfectly understood what it should be, because it's just an average of elliptical galaxy spectra, you can make significant errors in the photometric redshift estimation. Sometimes you can make disastrous errors also. You think it's redshift 5, but actually redshift 0.03. Okay, so you can go for a complete toss. Right. Okay, so this is with large area surveys, but you can also do pencil beam surveys. Here is one example. So here what you do is that you observe a very small portion of the sky, but you observe it to very, very high depths. So you can get at least photometric redshifts, if not spectroscopic redshifts. And they've tried to obtain in this field spectroscopic redshifts of galaxies at redshift 4, 5, 6, etc. And once you do that, then you'll get a slice of the universe. But that, because the large scale structure of the universe is not homogeneous on very small length scales, if you take a very narrow angular slice, you are subject to what is called cosmic variance, which means I do this small patch of the sky and I estimate something about galaxy evolution, and I go and measure another different patch of sky, but equally small, in another part of the sky. I will get quite considerable different values from the parameter that I'm measuring. And that is because of cosmic variance. Because what has happened is, along one line of sight, I have penetrated through some large scale structure. And on another line of sight, I've penetrated through a different large scale structure. And I don't have sufficient length scales in the transverse direction to take care of, to make sure my sample becomes homogeneous. So it's non-homogeneous, and therefore it becomes very biased. It has thing, but there are again statistical techniques to estimate this cosmic variance and try to minimize it and so on. But these kind of pencil beam surveys allow us to map the evolution of field galaxies out to redshift 1, 2, and beyond. Whereas the large scale structure, large area surveys, they're right now with SDSS, you can go to about 0.1, 0.2, and so on. A little bit information with BOSS, you can go up to 0.3 or 0.4. Here you can go well beyond redshift 1. And I will end with this slide, which is the future of pencil beam surveys. So about 3 or 4 days ago, NASA released the first image from JWST. It was an image of an ordinary star, but they didn't even release the actual data. They released the PNG version or the JPEG version of that image. But people downloaded that image since they knew which star JWST was looking at. So they knew exactly which patch of sky this is. They identified other objects in the field, some few bright galaxies whose positions they knew from previous surveys. And then they constructed what is called a word coordinate system. And then they posted that on the internet. So this is like completely unofficial data. But what you see here on the right is a portion of that bright star image spike is seen over here. That's that straight line. But I downloaded the FITS version of this data, and I also downloaded imaging data from something known as the DESI Legacy Survey. So on the left, you have deeper than SDSS image of the same part of the sky that you see on the right. And so for example, this star is this one. Okay, this one is actually this one. It's quite faint, but this one is this one, and this one is the one over here, and so on. So you see about 10 objects on the left-hand side DESI image. These are all galaxies, except this one, which is a star. This is probably a star. And whereas on this right-hand side image with JWST, just about, I think, 35-40 minutes of exposure time, they're able to see about, I think there must be about of the order of 50 to 100 objects over here, all galaxies, distant galaxies. We're seeing for the first time with JWST and released just 3 days ago. So this is the future of pencil beam surveys, because what they're going to do with JWST very soon is that they're going to point JWST in one direction and observe that same direction for 10 days, 15 days, and so on. So in 30 minutes, you got so many. If you do it for 15 days, you will get the equivalent of this Hubble ultra deep field that you see in this picture, except that it will have many, many more high redshift galaxies than what Hubble can detect. Because remember, as you go to high redshifts, your res frame optical emission gets redshifted into the near infrared. So you'll detect lots and lots of high redshift galaxies. So it's a mind-blowing time to live, and within the next year or two, you're going to have fantastic pencil beam surveys with JWST. Okay, so we will stop here. And so this is with the JWST NERCAM. And I think within the next 1 or 2 months, they will release officially this data. You don't have to do all this hacking and download data from random websites to make this image. But you can do it officially within a month or two. Okay. Are there any questions from the Zoom audience?
Hello.
Yes, please go ahead.
So, as far as the inhomogeneity on small scales is concerned, so on large scales, when we are seeing in past. So
yeah.
it may be possible that universe intrinsically was homogeneous, but gravitational interactions between these galaxies had introduced these homogeneities, inhomogeneities, and on the small scales.
Yes,
So
so
the
that is correct.
so the
We know that to be a true. We know that to be true.
okay, so sir, the smoothness that we see on the large scales, uh, is it due to this reason, or can it be due to this reason?
Yes. So in fact, the smoothness that you see on and we'll visit this again when we talk of dark matter. The length scales on which the structures are seen depends on whether you live in a cold dark matter dominated universe or a warm dark matter dominated universe. In a warm dark matter dominated universe, structures on smaller length scales get averaged out or washed out because the warm dark matter particles are called warm because they're kinematically warm. They're high velocity particles. So what happens is, if there is structure on small scales over a billion years or something with warm dark matter particles, that signal gets wiped out. So if you look at the power spectrum of the matter distribution, the spatial galaxy distribution, the predicted power spectrum from warm dark matter is different from the predicted power spectrum from cold dark matter cosmologies. And it was with the advent of surveys like the 2DF and SDSS that for the first time we had enough data to give ourselves a preferred model. And now that's why we say that we live in a CDM universe, lambda dominated cold dark matter universe, because the warm dark matter models are excluded by the structure that is seen in the galaxy distribution as observed by SDSS and 2DF. So yeah, you're right. So what you're saying is perfectly correct, that the structures that you see and the length scales on which you see structures are just gravitational manifestations of the time evolution of the galaxy distribution. So because of gravity, structures develop and they grow, and given enough time, structures do form on different length scales. And but as we know again from the CMB observations, for example, that the anisotropies in the CMB are very, very small. So on the largest scales, observed scales, you should see that anisotropic signal in the form of the acoustic oscillations imprinted on the structures of galaxies, and we do see that also in the Sloan survey in the form of this baryon acoustic oscillations. Yeah. Any other questions? Yeah. How do you say that something is a galaxy cluster or supercluster? There are definitions. I mean, they're not single unambiguous definition. Different people have given slightly different definition, but they're all related to the number density of galaxies above a certain mass or a luminosity in a certain volume. So if you say that the number of galaxies exceeds X per co-moving megaparsec, then I will call it a cluster. If it is between X and some Y, I'll call it a group, and otherwise I'll call it a field. So there are definitions like that. So when we look at galaxy clusters, we will encounter some of those definitions. Sorry? So the clusters are the largest gravitationally bound structures. Galaxy clusters are the largest gravitationally bound clusters we know of in the universe. The supercluster is not really gravitationally bound.